Yeah, so good question. I have just chosen that. I've picked that kind of out of the blue. Okay, so we have to say, all right, we're gonna sample these kids. How many kids do we want to sample? I've just chosen 9. Um, I chose it so that the math would be easy, but in reality, we have to choose that. Now later on in the semester, we can talk about how big should we make n, right? How many should we sample? For instance, in a polling, presidential polling, should we sample 1,000? Should we sample 10,000? What are we gaining when we change that n around? But yes, I've just made up n equals 9. Okay. So we have a normal distribution, and so now we can talk again about, in the behind me, we calculated what's the chance that we grab one kid, and it was 10.5 or older. Well, here, what's the likelihood that we sample 9 kids and the average is 10.5 or older? And so this is a little different calculation. The concept is the same, but we're dealing with a sample. And so now we're in the normal distribution, right? We can't use our uniform distributions to attack this question because we're over here. We've taken a sample, and so it follows a normal distribution. And so we have to go through z is equal to x bar minus mu of the x bars divided by the standard deviation of the x bars, or the sample means. And so, so that's the process we can find. Again, we know that this mean, this normal distribution is centered around 9, and has a standard deviation, right? It's got a certain spread to it, and we've calculated that as, the standard deviation is the square root of 3 over 3, or about 5 or 0.57. So what we're asking for is, how far away is this? If we were to take a mean and or a sample, and it came as a mean of 10.5, how far away from the mean of the sample means is that? And again, what we're really after is, how rare is it that we would get a value at least out here, right? That's what we're looking for. What percentage of the time when we take a sample of 9 will we get something that extreme, that far away from the mean? And down here is the square root. Square root of 3 divided by 3. Okay, and so what we end up with is, I kind of ran out of space, but we have 1.5 over square root of 3 divided by 3, which becomes 4.5 over the square root of 3. Right? We just flip that denominator up, and that is, it's right at about 2.6. Okay, and now what did we just find? We found the z-score of a sample mean being that far away from the mean of the sample means, right? When we take a lot of samples, the mean of all of those samples is going to be 9. And so what are the likelihoods that we take a sample and it's this far out? Well, that's 2.6 standard deviations away from the mean of the sample means. Let me pull up that's not what I want. That's redundant. I was going to pull up the z table, but for some reason they do not want to show that. Well, so you can look up the z value precisely on your own, actually. Let me just, we can do a display capture. That should work. And so we got a Z. Just zoom in here a little bit. We got a Z score of 2.6. So let's scroll down here. And 2.6, it's 2.60. So we get 0.4953. 0.4953. Just write that down. So, of course, that is not quite what we're after, right? We wanted to know greater than that. And so we just found that this area is 0.4953. And so we need to subtract that from 50%, leaving us with what? What is that? 0.0047. So a little under 0.5% chance that we would find a sample of 9, all of which sorry, not all of which, but the mean being 10.5 or greater. Okay, so with one individual, if we grab one kid, there's a 25% chance that the first time they trick-or-treated was age 10 and a half or later. But when we take a sample, that distribution gets tighter around the population mean, and so it's harder to find an average out of 9 kids that's all the way out there at 10 and a half. Okay. So let's walk through another example, feel free to jump in with questions if you'd like. Let's walk through another example, though, while we have this. And this time we're going to start with a normal distribution. Okay, so let's see. Let's just flip to a clean page. And what I'm going to do is I'm going to start with a normal distribution. Again, let's think about Halloween coming up. Maybe, well, I don't know if it's strictly Halloween, but we want a normal distribution, and we're gonna consider this the number of Pringles you eat, right, when you pop the lid off. And I think what's the old jingle? I don't know if Pringles are still a thing or still advertised, but it was once you pop, you can't stop or something. You keep eating them, and so it's pretty unlikely that somebody eats only 1 or only 2 Pringles. And in fact, what typically happens is maybe there's a mean of 10 and a standard deviation. So I'm making up these values, but maybe there's a standard deviation of 4. Okay, so right away we can kind of understand a little bit about how many Pringles people tend to eat. Right? Empirical rule tells us 68% are between 14 and 6, right? Just getting a sense as to the distribution. So when we are kind of presented with a normal distribution, the nice thing for you is that you don't have to calculate the mean and the standard deviation, because I kind of have to give you that, right? So in the uniform distribution, we had that step of crunching, this type of stuff. We already are kind of given those values here in the normal distribution. But what we might be interested in is, okay, again, how likely is it that somebody eats, 2 or fewer Pringles? And so we can go through the Z-score. Now, you may get a good sense as to what this is going to be, again, from the empirical rule. The empirical rule has a little bit to say about this if you follow it out a little bit further. And in fact, so 68% is between. So this is not that's quite confusing to draw it in there. This will not give us the exact value, and we'll turn and calculate that exact value here in a minute. But 68% is between 1 standard deviation, right? So really, kind of going down a rabbit hole here, but I think it's helpful. So really, it's 34% and 34, right, on each side of the mean. Within 2 standard deviations, what is our empirical rule tells us it's about 95%, right? So 95% is within 2 standard deviations, and we can sense that, we're talking about a value of 2 here, and so that's 2 standard deviations from the mean, right? That's 8 less than the mean, so it's 10 minus 4 minus 4. So it's 2 standard deviations away. So we think that there should be some connection to that 95% empirical rule. And in fact, as we'll see, it's pretty close. So let's go through and find the exact value. And we'll come back to this empirical rule thought here in a second. So what's the chance that a person opens the Pringles and they only eat 2 or fewer? Again, maybe they can eat some crumbs. So we'll consider this continuous, because you could eat 1.5, because there are always some broken Pringles in the can. And yeah, so let's 2. What's the chance that it's less than or equal to 2? Well, let's build a z-score. So z is x minus mu, right? We're dealing in the populations. So we're not talking about a sample yet. So z is 2 minus 10 divided by 4, right? And what we just said, that's -2. We're 2 standard deviations below the mean. And so for that one person, we can just jump to the z table. And let's scroll down to, again, 2.0, and we get 0.4772. 0.4772. Okay, and again, now that's not the end of our answer, because we need to return back to what are we trying to do? We're trying to find this value in here, and that 0.4772 is really the value. Sorry, I got a lot going on here. Let me just redraw that quickly. We are looking for this area, and what we've just found is this is 0.4772, and so we can subtract from 50%, right? So 0.5 minus 0.4772, because we know this range is 50%, right? Half of the distribution, it's symmetrical. And so we know then that our little window there is 0, what is it? 238. Did I do that right? That doesn't, I think that's right. 10, no, I've got too many. 2. How does math work? 228. Still could be wrong, but let's go with 0.228. Now, that's really close to the empirical rule, right? The empirical rule tells us 5% are beyond, or the empirical rule tells us 95% fall within 2 standard deviations. So that must mean that 5% fall without or outside of 2 standard deviations. But this is like 2.25%. So what's going on here? Well, remember the empirical rule is on either side of the distribution. So the empirical rule tells us 95% are within 2 standard deviations. That means 5% are on the outside, but only 2.5% on either side. Right? So the 5% is both sides. And so one end of it is going to be 2.5%. We're a little bit less than that, and that's because the empirical rule is kind of a rough estimate. And in fact, so we used a z-score of 2. We were 2 standard deviations away. The exact value that gives you 95% is not 2. It's actually 1.96. Okay, so I'm going to pull up the z table again, and it's 1.96, and that's actually what's shown up here. Okay, so 1.96 would give you a value of 0.475, which gives you 2.5% in this little white space. Okay, so the empirical rule is a rough estimate. It's helpful to remember, but the exact value is slightly different. But it's always good if you can put it in context of the empirical rule, because it gives you, if we start with the logic of the empirical rule and say, okay, I'm about 2 standard deviations away from the mean, so I should be thinking my answer is somewhere in this 2.5 or 5%, depending on what exact calculation you're doing. Then if you go through the whole process and it comes out 15%, it's kind of a red flag to say, okay, where did I mess in this? So the empirical rule is very helpful for kind of fact checking your answer. Okay, so this is back in chapter 7 world, right? We're just doing a normal distribution, but we're grabbing one individual. So what changes when we take a sample? Again, I'm gonna choose this again. We're gonna take a sample. Let's take that same sample of 9 individuals, and again, I'm just making that up. But let's say the sample is 9. What happens? Well, again, these samples are going to become a normal distribution. We already were a normal distribution, but they're going to become a normal distribution as well. And the normal distribution is going to get tighter than where we were. Okay, so let's draw out a normal distribution. What do we need to know? We still need to know what is the mean of the sample means and what is the standard deviation of the sample means, or the standard error. So n equals 9 is our sample size. So we're taking a sample of 9 people, right? Maybe we're watching 9 people open a Pringles can and see how many they eat. So imagining a sample size of 9. Again, what we're doing to build this distribution is imagining we do that, a few billion times, or however many different combinations there could be. So this distribution is all of the possible samples of size 9 that we could take. And it would be a different distribution if we took a different sample size, but again, it would remain a normal distribution. So the normal distribution that we're dealing with has a mean of what? It has a mean of 10, right? Again, the mean of the sample means is equal to the population mean. And so we have a sample size we have a mean of 10 on this normal distribution. And we have what's our standard deviation? Well, that remains the same as we calculated in the previous example, right? This process of moving from a distribution or a population distribution to the sample distribution is the same whether we're coming from, whether we're coming from a uniform distribution or a normal distribution or any type of distribution. We have to transform into this new normal distribution. Okay, and this is the distribution of all the possible samples that we could take. So this becomes, what did we say we had? We had a standard deviation of 4, and we are doing a sample size of 9. That's hard to read. So it's the square root of 9. And so we get 4/3. Okay, so this distribution has a mean of 10, just like the population did. But it's got a standard deviation, right? Kind of how spread out is this? It's tighter. It's 4/3 rather than 4. It was 4 over in the population. When we take samples, it gets tighter, right? It's harder to get those extreme values. That's one way to think about it. You can find a person that has, eats more than 16 Pringles, but to find a sample of 9 where the mean is greater than 16 is going to be harder, right? We have to have kind of more extreme outcomes. So this is our distribution. Now, if we want to think about a sample of 9, if we take one single sample, what's the chance that it is, again, let's stick with below 2, because I think it's helpful to to see how much harder it is with a sample to get that extreme. So we found with one individual, it was about 2.25% chance. What is the likelihood of finding a sample where the mean is less than 2? So less than or equal to 2. Again, we're in the z-score, but this time we are dealing with me in the way. That's what we're dealing with. So the mean that we're interested in here is 2 minus 10 over, what did we just find? It's 4/3. Okay, so you can see that, you can't see because I'm in the way, but our calculations here, 2 minus 10 divided by 4/3, is very similar to what we did in the population. And in fact, all that's happened is we've changed the standard deviation in between these two normal distributions. But that's going to have big repercussions as far as how likely this is. So we can finish this out. We get -8 divided by 4/3. And that let's see, that's going to be -6, right? So I think we get a z-score of -6. And let me that is going to give an extremely small value. I had a different value pulled up. So I'm going to plug -6 into an Excel thing to give you the exact value, because again, maybe I won't, because might be too far away. Well, I can tell you this, that it's going to be less than. So what is the percent likelihood that we are that far out, right? So we are talking about a value down here. What's the percent that we are that small in Pringles? So we took a sample size of 9, and they all, collectively, the average was less than or equal to 2. We get 0.000000. I know that it is less than this, because that's the value of 5.25, which I mistakenly had in my notes. So it's somewhere less than, there's 7 zeros there. So percentage-wise, it's, we're talking 0.0000076. So less than that percent. Okay, so extraordinarily rare that we would find a sample size of 9 that has a mean that low. Okay, so hopefully this gives you a little sense as to the difference that happens when we take when we're dealing with a population compared to the sample from that population. That distribution gets much tighter as we go. But the process, you can see the process remains the same. So one problem with that is that you kind of have to keep your head on swivel as far as which standard deviations you're supposed to be working on. So positive that it's kind of one process to learn, but negative that you can get confused between the two very, very easily, right? And obviously, when you go down the wrong route, you can get wildly different answers. This is essentially 0, whereas there is a chance that you'd find an individual that low. Okay, so I want to turn for the last 20 minutes or so, where did the negative, when looking at the -2, the 10 minus 4/3. So so this 2, perhaps this is, this 2, if this is what we're looking at, or there's a lot of 2s. So let me just walk through them. So this 2 is what I've chosen, right? So we were interested in what's the chance that we take a sample size of n and the mean is less than or equal to 2? So I've kind of made that up. Again, we could have picked anything. We can recrunch this and say, what about less than or equal to 8? And then we would plug in 8 here. Okay, so it's whatever we're interested in. Or we could say between 8 and 12. Right? We can. This is us picking what window we're interested in. And so, this too is this sample mean that we're choosing. Okay, so we can recrunch this for any value. We could plug in 8 minus 10 divided by 4/3, and that would give us, this larger area. So hopefully that clears that up a little bit. So I had chosen less than or equal to 2, simply to kind of show, because we had just done it over here in terms of one individual less than or equal to 2. Hopefully that clears some things up, but good question. Okay, so I'm going to pull up the Excel. And again, if you joined late, this is on the Canvas site under Chapter 8. It's called Playing Around with Playing with the Central Limit Theorem. You don't need to pull it up, but if you'd like to, or if you'd like to pull it up later, feel free. Yeah, so we won't. There's a lot going on this this file, so we won't get to everything, but hopefully it'll give you some visual as to what's going on. Because again, what we it's going to be helpful if I get this to okay. So again, we kind of we're playing around with a few different ideas here at the same time, and so hopefully it'll be helpful to see this in action. Let me just try to get you the best view. It's pretty good, but I would like to still see you. Okay, so yeah, so there's a lot going on in this file, and there's again, always feel free. This is downloaded, or it's uploaded to Canvas. So if you mess something up, you can always re-download it and start fresh. Or as we talked about in previous weeks, you can always make a copy of it, of the sheet. If you go down and move or copy, create a copy. Right, so you can make a copy, and then you have a new sheet to mess up, and you can always jump back to the last. Okay, so I just want to quickly talk about what's happening in this, and we'll see if it helps some of these concepts sink in. So a lot going on. What I'm doing, and Excel is great for a lot of things, but this is not its strong suit. So there are other statistical packages which would do this a lot cleaner, but we're kind of playing around with Excel, trying to get our feet wet. So hopefully it's instructive to see some Excel in action. So first, what's going on here on the far left? So I have just been creating, let's see, so I have 2,000 observations here. And I have a few different distributions happening. So in the white here in the middle, it's just kind of an even uniform distribution from 1 to 100. So because there's 2,000, I have 200 values. Sorry, I have 20 values of 100, 20 values of 99, etc. But we're going to deal more with the random distribution. So this is, I'm using the random between function, and that's going to give me just a random number between 1 and 100. And actually, kind of wish I would have done 0 and 100. Is that going to mess everything up? It probably would. So I'm going to keep it there. So again, each of these is going to spit out a random number 1 to 100. Now, as we've talked about in the past, Excel the formulas in Excel update every time you change the sheet unless you turn that setting off. So anytime I change the sheet in any way, it recrunches. So you can see the values change in Excel. So that's something to keep in mind. Now, I have also built a normal distribution using some... You can comb through this, but rest assured that this is a normal distribution, so there's a certain chance that it falls between certain values that spit out a normal distribution. So what does this all have to do with the central limit theorem? Well, we're going to roll over here and look at some graphs. So this is the distribution of that. I tried to kind of color code things. So that's the distribution of that random uniform kind of distribution. So it's not perfectly uniform, but it's some distribution of the population that's roughly uniform. Okay, it's going to change again every time we update. It should have changed. I don't know exactly what happened there, but maybe this is not updating. Always bugs to be found. So anyway, we have a distribution that's roughly uniform. And what we want to show is when we take samples from that, it becomes a uniform, or it becomes a normal distribution. Okay, so what I have built down here now is sampling. So I'm taking a number from that column over here. Okay, bear with me. The results are coming. So each value here, or each cell, takes a random number out of that whole table. And again, it's going to recalculate every time. So you can consider this first row as a sample. We're taking a sample of 25 values from that column. Right, so here we are grabbing 25 values from the column here of the uniform distribution. So when we take a sample, we get a sample mean, right? And so that sample mean of those 25 is about 57, okay? And that's larger than our population mean, which is this time 50.8, right? We can expect this to actually be, usually be 50.5 or in that range. Again, there's a little, I didn't make it clean uniform. But if the population has a mean around 50.5, these values, these samples are going to jump around, but they're going to be centered around that 50.5. Okay, so again, to read this, we kind of have this row is a sample. In practice, we take one sample, but what if we take all of the samples or a lot of samples? So I have pulled this down. So this is, sample 23 is this row. Sample 28 is this row. And if we scroll down, I have this set up to take 240 samples. Again, we could draw that down and take 1,000 or 10,000 or something. So if we take all of those samples, we then have a distribution of samples. And that is shown up here. So I have a frequency table. And I've done this a little different. I'm using the frequency function, but in an array form. So if you're playing around with this, it'll yell at you. So you might have to look up what arrays are in Excel. So that'll be interesting, maybe for some of you. So when we do that, when we plot it out, so here we're taking sample sizes of 25. We're taking those samples from this orangish peach distribution. We're taking 25 out of this distribution. We're running a sample mean. We're doing that 240 times, and this is the distribution of all of those sample means. Okay, and you can see it becomes a normal distribution. Again, this is only 240, so it might be cleaner, or maybe I should have pulled it down to 1,000 or something. But we can see the distribution become a normal distribution, and it varies a little bit every time we update the sheet. It's not, again, with only 240, it's not perfectly normal. It still has a little movement, but you can see that in action. And now what if we don't sample 25? What if we sample a smaller number? What can we expect? What does the central limit theorem tell us? Well, the central limit theorem tells us it still is a normal distribution. But what we found is that distribution, the normal distribution that we deal with, the standard deviation depends on the sample size. So I've redone the process this time, taking a sample size of 9. Okay, so here what I've done is I've just selected the first 9. Okay, so to get around it in Excel, that's what I've done. So we've take the first 9 random values that we've chosen and do that all the way down. So we have 240 samples of 9. And we can see that up in the green distribution. So n equals 9. If we were to take sample sizes of 9 over and over and over, we still get a normal distribution, but as we can expect, it's a wider distribution, right? The standard deviation is bigger because we're, again, thinking about, let me see if I can do this on the fly, thinking about the, try to put this up here. That did not work. That was supposed to be there we go. Sorry about that. So why does this change the way it does? Well, remember the standard deviation of the sample means is the population standard deviation divided by the square root of n. And so in our case here, it's the population standard deviation divided by the square root of 9. Whereas down here, it's population standard deviation divided by the square root of 25. Okay, so of course that's going to be a smaller standard deviation. It's a tighter distribution. So we expect it to be more clumped in. Okay. Just gonna try. Maybe we can see this get cleaner if we pull this down a ways. It's entirely possible that I'm gonna mess this up and we're gonna not get much out of it, but let's see what happens if we pull down somewhere, I might have also frozen Excel. It might have, okay, there we go. So what happens if we pull these down? So we should see a little cleaner of a distribution, okay? It should get rid of some of that fuzziness that happens just because we have only 240 sample. Oh, of course, we overshot. Okay, so what we'll look at after this is that this also holds true for a normal distribution. Let's see if Excel can catch up. But again, that the difference between the two distributions is going to remain true. Not looking great. There we go. So we have just under 1,000. I think I need to update these. Okay, so bear with me. Again, Excel, not the cleanest for this. If you were playing around in R or SAS or something, there'd be some kind of quick ways to do this, but we can get there. I don't know if we need to clean that up. So, yeah, we get a cleaner look. Okay, so yeah. So this is going to be less jumpy because we have a full 1,000 to look at. Still possible, right? We can still see that you can get values out there, right? We calculated there's a 0.0004% chance or something of these extreme cases. And so you can see those cases happen more likely when we have a sample size of 9 than when we have a sample size of 25. Okay, so that sample size tightens up this distribution. And again, the same thing is going to hold true. Sorry to keep whipping you around the screen, but I have a normal distribution over here going through the same process. So here's the population, again drawn from that column, the original column. Let me get rid of that. Normal distribution, let's take some samples from it. Same thing over here, drawing some samples. You can play around with that if you want to look at it more. But what happens to the distributions when we think about 9 versus 25 on the sample size? And again, we get a tighter distribution when we have 25 versus when we have 9. Now, it does get tighter more quickly, right? So our uniform distribution was more spread out. The standard deviation of that uniform distribution we could calculate quickly, but that's going to be a wider distribution than our normal distribution, right? So we start from when we think about well, that's really not working. When we start from thinking about the standard deviation of the sample means, this standard deviation in our normal distributions here is a tighter one than we had in the uniform distribution. And again, we could probably crunch that, but we won't for sake of time. But again, regardless of where you start with the normal or with the standard deviation, as you increase that n, it's going to be a tighter and tighter distribution. That's going to be helpful to kind of keep in the back of your mind when we move forward into the next few chapters as well. That not only do we get a normal distribution, but the fact that we can get tighter and tighter is going to be important moving forward. So I know this was a lot in this Excel to throw at you in 20 minutes, but hopefully seeing it in action, taking multiple samples and plotting them gives you a little bit of experience with seeing this. Feel free to play around with this. If you have questions, if you're curious about how I did something in Excel or why I did it, if you find an easier way to do this in Excel, please let me know, because this is not this can't be the simplest way. But a lot of what we do in Excel is figure out something that works and go with it, only to in the future find something that's easier. Yeah, so we'll see. Maybe we might even return back to this when we dig deeper into the next few chapters. So just to give you, I know you all have, many of you probably are early on in the Connect homework. So you're not even really thinking about next week. But next week we are dealing with what happens when we don't know the population values, right? We've been drawing upon the concept that we can grab, this relationship and the one we just had drawn, right? We've been pulling our normal distribution from this info, but what happens if we don't know what the population is, the population values are? How do we tackle that? And that's where we turn to next. And again, that's a lot of where we are when we actually go through the process of sampling. So our examples thus far have been we're assuming that we know certain things about the population, but as you can see, we'll in fact, next week we can talk about sampling, where you don't know, so such as presidential polling or candidate polling data. We don't know the population mean, so how do we tackle that given that we don't? And that'll be timely as we are now, a week and a half from the election. So, yeah, I think we'll end up there. If you have questions, I'll stick on for a little bit. I'll have this posted again later today. I think my mic may not have been recording early on, so there might be either silent me, which you might enjoy, or I might dub over a little bit. But you can look for that if you want to go back and look at what I've done. Otherwise, I also have office hours later today, so if you're looking for to walk through some more examples, we can do that or answer some questions.